started now. So, welcome everyone to the first edition of the ACM Research Symposium. ACM Research is a brand new division and semester-long program designed to promote a structured research environment for students. And tonight we'll have 4 teams showcase what they've developed throughout this semester. And then before we begin, I'd like to take the time to introduce myself, our amazing team, faculty advisors and judges for tonight. I'm Ryan, I'm the director of ACM Research. Our team, moving on to our research leads, I want to thank them for all their hard work they've put in every day. They've done an incredible job, and without them, this program would have never been possible. So first we have Shreya leading the phishing attacks team, and then Aditya leading the CNN image classification team. And then we have Brian leading the NLP text summarizer team, and then lastly, Bryant leading the salient features in VR streaming team. Next, I'd like to introduce and thank our faculty advisors for volunteering their time outside of work to help our team succeed and learn more about research. So over the summer, we originally had 1 faculty advisor for each team, but that didn't go as planned. And as a result, we were left with 1. I know Dr. Prakash is watching right now. So we're extremely fortunate and grateful for Dr. Prakash to help advise the salient features in VR streaming team. Thank you very much, Dr. Prakash, for taking the time out of your day to help your team. We sincerely appreciate it. Claps. Yes. Lastly, I want to introduce and thank the judges for coming and helping out tonight. We greatly appreciate your time and effort in making this symposium possible. First, we have Dr. Gupta, who is a professor at UTD and the previous CS department head. He's greatly helped ACM for many years, and we're super grateful to have him here today. Next, we have Dr. Ovidiu Dayescu. He is the current assistant department head of the CS department at UTD, as well as a professor. Last but not least, we have Dr. John Cole, who is an associate professor at UTD and the faculty sponsor for ACM. All right, that concludes the introductions. I am now going to stop sharing my screen, and then we're going to have our 4 teams present tonight. To begin, we'll have the Analyzing Phishing Attacks team go. So best of luck, everyone.
All right.
You all should be able to see the screen. Got it.
Yes, you are good to go, Eric.
Good to start. All right. Hello, everyone. My name is Jesse. Our project is analyzing the targeted nature of phishing attacks. My team members are Abigail, Jerry, Egan, and Eric, and our group was led by Shreya. Many students at UTD receive an enormous amount of phishing emails on a regular basis. Phishing emails that are sent with malicious intent, are annoying but yet extremely dangerous to impressionable individuals, most notably college students. The senders of phishing emails will usually pose as a reputable company or department to gain the trust of an individual in order to obtain their personal information. Information like social security, date of birth, passwords, or even answers to common security questions. Our project, Analyzing the Targeted Nature of Phishing Attacks, aims to address the issue of phishing attacks that target college students. Our goal is to research factors that cause college students to be targeted by phishing emails and how likely are college students to fall for phishing attacks. We approached this problem from 2 fronts. We first conducted a survey to research student responses to study their awareness of phishing emails and how likely are these students to be deceived by phishing emails. Next, we created our own analyzing and detecting script to better understand how an automated system might be able to combat these phishing attempts. Abby will now discuss the first component of the project, the survey.
Thank you, Jesse. When discussing how to observe and analyze the behavior of UTD students when faced with these phishing emails, the team decided to create a survey that asked students for their opinions on a set of 8 phishing emails and 2 non-phishing emails. We structured the survey in a way to eliminate as much bias as possible when participants took the survey by establishing parameters that include no backtracking to prevent survey participants from changing their answers after seeing other emails, a 15-second time limit to view each email per our research that emails are looked at for about 12 seconds before they are decided on to be phishing or non-phishing by a user. And we randomized the order of phishing emails in order to simulate a more natural environment where phishing emails may be scattered among real ones. And now I will be discussing the results of conducting our survey. We asked survey participants about the likeliness that each email shown to them was a phishing email. And after observing the data, as you can see on the right-hand graph, we came to the conclusion that many people were able to predict phishing emails easily, with almost 45% of participants deeming the phishing emails as extremely likely to be phishing emails, and almost 35% of participants deeming the phishing emails as somewhat likely to be phishing emails. However, this leaves about 20% of participants that were not able to discern the malicious nature of these phishing emails. And on the other hand, when looking at the non-phishing email data on the left-hand side, participants were more split on whether or not the non-phishing emails were phishing emails or not. And this was most likely because participants may have had a rising suspicion of all the emails shown to them as a result of the nature of the survey itself, which is a symptom of creating a survey to gauge responses. And now Jerry will discuss the process of creating our email parser.
Thank you, Abby. So in the beginning of the project, we explored a number of different ways of getting data from raw emails. One of the alternatives we came upon was mailparser.io, an online API which claimed to provide an easy solution to extracting the data that we wanted. However, after doing some research, we discovered that mailparser.io would not be optimal for our needs due to price and lack of customization. So we decided to create our own parser to fit our needs. In addition to the basic extraction of fields from raw emails, our parser also performs a number of other tasks, including HTML filtering, using Beautiful Soup, as well as reading text from images and GIFs using OpenCV and the optical character recognition engine Tesseract. The parser then does some noise removal to enhance and fix the data. After getting useful data from the email files, the parser uses the TextStat and TextBlob tools to generate multiple readability scores and perform sentiment analysis on the text. We ran our parser on 83 phishing emails and 292 non-phishing emails in order to get our data set. One of our main challenges was our limited sample size. The emails we ran the parser over were only gathered by the members of the group, so there didn't end up being a lot of phishing emails compared to normal ones. Another problem we faced was frequent duplication of emails, which skewed our word frequency analysis since some words only apply to a small subset of emails. Many of the emails also had unstandardized formatting, which created a number of edge cases that we had to handle individually. Using the parser, we collected important statistics and information about phishing and non-phishing emails, which Egan will now discuss in further detail.
Thank you. Once we had our data in a more readable format, we set about finding interesting trends in the dataset. We began based on the survey results and our own observations, finding individual characteristics at least partially separating phishing and non-phishing emails. An example would be the domain of the sender email, graphed in the top right. The majority of phishing emails come from public email services, while the majority of emails received by a UTD student comes from a private domain. One predictor that performed far less than expected were the results of established authentication methods SPF, DMARC, and DKIM, graphed in the top left, which passed phishing emails at a higher rate than non-phishing emails. As we accumulated more distinguishing features, it became helpful to get a more accurate predictor by combining predictors into a single metric. For categorical measures, we assign numerical values based on the proportion of phishing or non-phishing emails. We aggregated numerical values into a single metric using linear optimization. One inconclusive and one useful aggregate metric is graphed on the bottom. The table below contains metrics we considered, as well as reasons for accepting or rejecting them as useful. Based on the results of linear optimization, it became clear that some of our individual metrics were too specific to a small subset of our data with high duplication. For instance, consider the phishing email word cloud on the right. The word arrival appears very large, but it only exists in a small subset of emails that are near duplicates and has been removed from the words we check. Once we removed those tests, we came up with our final metrics presented by Eric.
Thank you, Egan. Using the data that we got from the previous step, we were able to calculate 3 scores, and I'm just going to go over those 3 scores really fast. The first one is the word frequency score. This score is calculated using the occurrences of various words frequently found in phishing and non-phishing emails. And the idea is that the more likely an email is to be a phishing email, the higher this score will be. So if it has more occurrences of phishing words, then the score will be higher. Whereas if it has more non-phishing words, then you might have a negative score. We also had the source score, which is determined by the source of the email. This is related to the public and private domain that Egan was referring to earlier, and they're split into UT Dallas, personal, and unknown domains. And our final score is the reply to score, which is another discrete variable, and it represents whether or not the reply to field matches the sender field. Again, we got 3 categories from this measurement. One was reply to not specified, another was reply to matches the from field, and the last category is reply to does not match the from field. We were then able to graph these 3 scores into a 3D coordinate plane in a scatter plot, and I'm just going to show an interactive version really fast. So this is the interactive version that we were not able to display on the static poster. And as you can see, there are essentially 9 clusters here that we can look at individually. And you can see on the x-axis, we have the word frequency score, y-axis is the source score, and z-axis is the reply to score. And the blue emails or the blue dots are phishing emails, and then the orange dots are non-phishing emails. We also have some red dots here representing false positives and false negatives. So looking at these false positives and false negatives, we are able to compare our script with the current solution, which is Outlook's general purpose spam filter. And we were able to detect 90% of phishing emails while incorrectly labeling only 0.68% of them, mislabeling 0.68% of non-phishing emails as phishing emails. And both of these rates are better than Outlook's spam filter. To conclude, from our survey results, parsing tool, and detection tool, we were able to deepen our own understanding of the underlying motives and characteristics of phishing emails, specifically those targeting college students. Our analysis also demonstrated the prevalence and danger of these targeted phishing attacks, and by analyzing these various features, we were able to create a detection classification script that captured 40% more phishing emails than the current solution, which again is Outlook's built-in general purpose spam filter. Outside of data and analysis, we are also able to raise awareness and about these targeted phishing attacks through our survey. And we hope that our findings will help colleges to identify and combat phishing emails to better protect students. We'll now open up for questions.
So this is Gopal Gupta. Can I ask a quick question? So basically you collected the data and you ran some kind of machine learning tool to create a model, I guess.
Yeah, I can answer that. So what we did, we didn't have machine learning in our programming. If you look down here at the data extraction, I think Jerry might be able to talk a little bit more about this after me. But the data extraction part, there is some sentiment analysis and language analysis being done here, but these are all third-party libraries. We simply extracted as many features as we could from this email and then applied some machine learning-esque techniques, but not really like machine learning to determine if it was phishing or non-phishing.
And was this, was this automated that you extracted the features and then you'll automatically check for presence of those features, or?
Correct, yes.
Okay, that's good.
I do have a question too. Did you try to compare with any other software that was developed to do similar things? Maybe for a different target, but do similar things.
Yeah, I can take that again. So we were not able to find a software that really did the same stuff. And honestly, it's a little bit difficult to do that because this is specifically, we wanted to tailor it specifically to UTD student emails. And there's not really a software that does that right now. We did notice that Gmail is better than that, but that's not the solution that we currently are like able to access. So we decided to build our own.
Gotcha. Yeah, because these are embedded, right? Like you said in Gmail, I guess UT Dallas also has a software that's screening the emails that we receive. That's why so many go to junk. So,
Yeah.
I mean, there are other things out there. I was just curious. Thank you very much.
I could add on to that answer. Part of the challenge is that a lot of the existing solutions have access to more information than we do, such as the recipient's past communications. So they're able to use some other tools than we have. So I think we did a pretty good job based on the information we have access to.
Well, I'm not saying you didn't do a good job. I mean, that's far from me to say. No, I think you did a great job. I was just curious if you had access to anything to compare to. Thank you.
So one last question, if I may. The language analysis, I'm not real clear on. One of the things I've observed is that, for example, phishing emails tend to have poor English, to put it mildly. Is that something you kind of did? Or what kind of language analysis did you do?
Yeah, we did perform language analysis using like incorrect grammar and stuff, but those results proved to be, I guess, inconclusive because they didn't really distinguish phishing from non-phishing. So,
Okay.
I mean, I guess it doesn't really meet expectations, but that's how the data turned out.
Yeah, and I can add on to that as well. So one thing that we noticed was there are some professors who send emails where they like maybe miss some like a period here or there, and our language analysis tool wasn't able to distinguish like a misspelled word that's on purpose versus like a misspelled word, or like not on purpose, but a misspelled word from a professor versus like a misspelled word just like from a phishing email, right? So
Okay.
people made errors on both sides, and that wasn't really a good deciding factor for us.
Okay, thanks.
Okay, that is all the questions we have. Thank you, everyone. Thank you, phishing team. Woo! Next up, we'll have the CNN image classification team.
All right, I think it's working. All right. Hello, my name's Aaron Chang.
I'm Alec Lowe.
I'm Anusha Saha.
I'm Viswa Raj. And Vivaan, are you having any? Vivaan, you're muted, actually.
That's my bad. And I'm Vivaan Shah, sorry about that. And we're the CNN team. And we use the convolutional neural network to classify retinal OCT images. But first, what is OCT? So OCT, or optical coherence tomography, is a retinal imaging technique which shines light into the eye and uses the reflection to build a cross-section image. This cross-section image is used to look at different areas of the retina and identify abnormalities to classify diseases. For our project, we decided to look at 4 types of classifications: choroidal neovascularization, or CNV, diabetic macular edema, or DME, drusen present in age-related macular degeneration, drusen, and a normal retina for comparison. Below, you can see a retinal OCT image of each of these types of classifications. Next, I'll pass it on to Vishwa to talk more about the data set we used.
Hey guys, so I'm going to tell you a bit about the data set that we used for to build our convolutional neural network. So the data set, as Vivaan just mentioned, was split into those 4 classifications, but beyond that, it was actually published on Kaggle, where it was then utilized by our team. So right here, there's a bar graph of the number of images in regards to the each classification. And as you can see, there's kind of a disparity between the C and B classification and like drusen, for instance. And the way we accounted for that, I'll touch upon it a bit later, but we did end up accounting for that. Now to talk to you guys a bit about the source and the verification of the data, there's also a couple things to touch upon here. first is that the OCT images were sourced from a wide variety of institutes, UC San Diego, Shanghai First Eye Institute, to name a few. Beyond that, every image went through a tiered grading system with several graders to ensure that every image was verified correctly. And beyond that, there was an additional validation subset of around 1,000 scans that was graded by 2 ophthalmologists. So they also made sure that the images were accurate and that the data that we're pulling from Kaggle is all legitimate. Now I'm going to talk a bit more about the models that we used and how we sort of built them. So our models are constructed through Keras from TensorFlow, and we use sequential modeling sequence in order to build it. That allowed us to experiment with a different set of layers, sort of mess around with that and try a variety of things. So the metrics we included and that we measured were accuracy for one, just how well the model does, the F1 score. And this is going back to what I previously mentioned about, that disparity between the number of images. The F1 score actually helps us, resolve that issue by giving us the actual accuracy, when taking that into account. Beyond that, we also measured the sparse categorical cross entropy loss metric, which allowed us to, sort of understand how well our model actually fit the data. Now I'm going to hand it over to Alex to talk to you about our CNN models a bit more.
All right, thank you, Vishwa. So before I talk about our model, I want to first explain what exactly is a convolutional layer. So imagine we have an image from our test data set. And so that that image could be classified as DNV or JSON or whatever. And so we break that image down into what we call an image matrix off of grayscale values. And so what a convolutional layer does is that it acts as a kernel, or in this case, a smaller matrix. And what that matrix does is that it traverses through our image matrix, performing specific operations. As you can see here, this one performs element-wise operations and multiplication. And ultimately, it outputs to what we call a feature output matrix. And so usually in CNN, it helps to have multiple layers of these convolution layers. So we could have a more accurate depiction and prediction for our classification. And so in our models, among our best model was the 1 million CNN model. And so this model in particular had 3 convolution layers, 3 max pooling layers, which a max pooling layer essentially takes the maximum value within that kernel. And then ultimately we had 3 dense layers. And so as you can see, we did a fairly good job. The model did a fairly good job having an accuracy of almost 94%, a relatively low loss score. Ideally, you want to have a low loss score, or else if you have a high loss score, that means your model has a lower probability to classify correctly. And we also had a relatively high F1 score. Ideally, you want to keep that as close as 1 to possible. And as you can see, we did well in that department. And we also had a relatively low number of low parameters with 1.6 million. And so after that, we decided to sort of experiment with different types of layers and different types of models. So for instance, we had the 6 million CNN model, which essentially had a fully connected layer at the end, which is essentially the same thing as a dense layer. And we also had the 15 million CNN model, which had an additional number of dense layers. And so, yes, the accuracy did a little better, but our loss score was also a bit higher as well. And according to the graph that you're going to see next, we had a huge increase in the number of total parameters. And so we kind of wondered, the 6 million model in particular increased immensely in terms of parameters, but we only had a 1.29 increase in classification accuracy. For the 15, it was even worse. We had a lot of parameters, and we only got a smaller number of increment of 1.08 in comparison to our 1 million parameter model. And so in conclusion, the reason why we chose our current model was because we thought that the trade-off between performance, such as having a higher total parameter value in exchange for a small little increment of accuracy, wasn't enough to justify switching our model. And so I'm going to pass that on to Anusha, and she'll explain what exactly is a dense layer and also our dense models.
So we also decided to train a few models that used a dense neural network rather than a convolutional neural network. So a dense neural network consists solely of fully connected dense layers where each neuron in a layer receives input from all the neurons in the previous layer. So a densely connected layer would provide learning features from all of the combinations of the features in a previous layer, whereas a convolutional layer relies on consistent features within a repetitive field. So in this particular example, the green nodes represent the input neurons, while the purple nodes represent the neurons in the hidden dense layers, which there are two of, and the pink nodes represent the neurons in the output layer. There's three of them since there are three prediction classes. So now on to our dense models. So our first model is our 500,000 parameter dense model, which consists of a flattening layer and 9 dense layers. So we found that our model performed with a rather low accuracy of 0.4256, a loss of 1.3782, and an F1 score of 0.1194. So its accuracy is 51.19% lower than our 1 million parameter CNN model. And our next model is our 1 million parameter dense model, which is similar to our 500,000 model, but it has 3 times as many parameters. So we found that this model performs significantly worse than all of our previous models, as it reaches an accuracy rate of 0.25, which is 68.75% lower than our 1 million parameter CNN model and 17.56% lower than our 500,000 parameter dense model. So surprisingly, increasing the number of parameters of our dense model only caused it to perform even worse than our baseline 500,000 parameter dense model. So this suggests that dense models lack certain localized spatial information, which is critical to this task. So now I'll pass it on to Aaron to show the demo.
All right, guys. So I'm basically going to showcase the collection of all the work that we've done over these past few weeks at ACM Research. So here's our collab notebook that we have pulled up. We download the model from our GitHub, and then we load it in. And then here we can see a summary of our model with the rescaling layers, convolution layers, and so on and so forth, as explained by Alex. And we can see the 1.6 million total parameters right here. So basically, if we were an ophthalmologist and we had a couple of patients' OCT scans that we want to classify, we would just load them in, drag them in, and it would load into our model, and our model would basically instantly predict and grade each retina scan. So as you can see, the first one loaded in was CNV and was classified correctly, DME classified correctly, and so on and so forth. So what this basically allows is it allows for ophthalmologists to get an OCT scan and have less downtime in having to manually grade these images and diagnose what retinal disease that a certain patient has, allowing them to put their effort into some other patient care that they have to do. So what does this all mean? Over 10 million Americans are affected by retinal disease every year, and even more worldwide. Our novel solution helps reach a 94% classification accuracy, and it allows for ophthalmologists to more efficiently and even sometimes more accurately classify these retinal scans. One of the things that we have to work on in the future is countermeasures against false positives and negatives. While 94% classification accuracy is very high, it still allows room for error. One of the major things that we can do to counteract this is allow for hyperparameter optimization, which is something that we were not able to work on during this project. Things include Bayesian optimization or implementation of random search optimization algorithm known as hyperband. And this would allow us to reach up to 97%, 98% classification accuracy in my testing. And this would greatly decrease the amount of false negatives and false positives that come up. And in conclusion, I would like to thank Aditya and Ryan and everyone else that helped us put this together. And me and my team would like to thank everyone for coming. And I would like to really thank Aditya for mentoring us during this whole program. I'd like to thank everyone for coming out. Any questions?
Yeah, so if I can go first. So how did you learn about CNNs? Did you take a class or on your own?
So Aditya, during this program, the first about 3 weeks, Aditya actually just gave us a bunch of lecture notes, and he was the one that taught us all this theory, all this machine learning theory within like 3 weeks, I think. And then we also had to do a lot of self-learning by ourselves.
And how did you choose this problem to look at, this related to retinal disease?
Well, so OCT classification, medical imaging classification is obviously a big problem within the machine learning subspace. And we chose OCT classification because as we're quote unquote beginners in this, the data set was very clean and well documented, and we were able to compare our solution against other Kaggle notebooks that were created by other creators. And we actually found out that our Kaggle notebook actually beat a bunch of the other ones using our own model architecture.
I see. So it's basically clear. I mean, a data set was available that was nice and clean, and okay, sounds good. That's a good reason. Yeah, sure. Okay, yeah, I'm done.
Any other questions?
Okay, I guess that's all the questions we had. Thank you, CNN team. Next up, we will have the NLP text summarizer team.
Can everyone see my screen fine?
Yes, you are good to go, Rick.
Thank you.
Sorry, I was on mute. I did not realize that. Okay. Hi, guys. This is our research project. We're the text summarization team, and our project is about making sense of the state of the art. I'm Varun Joshi.
I'm Rick.
I'm Fawaz.
I'm Aditya.
I'm Dylan, and our research mentor is Brian.
Okay, so what is text summarization? Text summarization is basically taking a piece of text, running it through a model, and getting a summary out of it. There are two different types of models that you can run your text through. One is an extractive model, which is like highlighting pieces of the text and then compiling that into a summary. On the other hand, there's also abstractive models, which are like paraphrasing the text and then using different vocabulary to form a summary. So how did we approach our research project? While we were researching, we found out that researchers in this field have been focusing on improving individual state-of-the-art models on benchmark datasets. So there was little analysis being done on comparing models together and finding out their strengths and weaknesses relative to each other. So what we wanted to do was to make sense of these models. And we did that by compiling 5 different models, and then we ran them through 2 different and diverse data sets. And in the end, we produced an accuracy score, which helped us gain insights and also discover the limitations that the models had. And now, in order to better represent the problem, Fawaz will now introduce some important NLP terminology.
So to understand rogue scores, which is what we use to evaluate our summaries, it's important to understand the terminology of n-grams. N-grams in NLP are basically groupings of n words. So as you can see in the diagram, a unigram is a group of 1 words, a bigram is a group of 2, a trigram is a group of 3, and an n-gram would be a group of n words. This is important in NLP because sometimes just looking at 1 word doesn't give us the full context. So it's important for models to look at bigrams and trigrams to get the context of the words. And now talking about rogue scores, which is what we use to evaluate the data. A rogue score takes in a golden summary, which is a human written summary, a perfect summary in a sense, and it compares it to the summary created by a model, and then it gives us a score. So we use 3 of the rogue scores, rogue 1, 2, and L. Rogue 1 compares the number of unigrams between those summaries, Rogue 2 compares the number of bigrams, and Rogue L compares the longest common subsequences. And the scores it gives us range from 0 to 1, with it being closer to 1 being a perfect summary. And now Rick is going to talk about the data sets that we used.
Yeah, so many of the text summarization models are trained on datasets in the news domain. So we wanted to find a dataset that wasn't news related. So we looked into 2 varying types of datasets. Our first dataset is the State of the Union speeches. And the reason why we chose this dataset is because of how diverse it is in terms of style and language. And there's speeches ranging from 1790 to 2019. However, the main problem that we faced with this dataset is that there was a limited amount of pre-existing summaries for these speeches. And without these summaries, it makes it much harder for us to gauge how well our model generated summaries performed without a reference. Our second data set is the Reddit TFU data set. And Reddit TFU is a forum where users post when something bad or unfortunate happens to them. And the main characteristic of this data set is that each post has a human generated summary at the end that we can use to compare as a reference summary. Another characteristic of this data set is that the writing styles are non-standardized, which means that there's a very varying writing style from each post. And we can use that to gauge how well our model does and expose any weaknesses. Here's a table of models that we analyzed and researched. So we analyzed 2 extractive models and 3 abstractive models. And all the models except for Spacey were transformer models. And the main difference between each model is that they differ in how they characterize each word and how they generate the summaries and how many parameters they use for generating the summaries. Here's a bigram distribution for 2 of the news data sets that we were mentioning earlier, which is the CNN Daily Mail and Newsroom. As we can see in these data sets, the bigrams are mostly located within the first 25% or beginning of the texts. And if we compare the bigram distribution to our data sets, we can see that our data sets are much more uniformly distributed. And because our data sets are more uniformly distributed, the models that were trained on news data sets, which were trained to extract information more from the beginning of the text, we found that those models performed worse than models that were not trained on news data sets. Here's an example of the BERT extractive model. And the BERT extractive model also is trained on the CNN Daily Mail dataset, which means that it mostly gets the information from the beginning of the texts. So we also calculated the rogue scores for the Reddit TFU. And as we can see, the blue models represent the extractive models and the green represents the abstractive models. And for the extractive models, BERT performed best for the unigrams, which is rogue 1, but overall Spacey performed best for extractive models. In the abstractive models, we can see that Pegasus TFU performed the best. But the problem with that is that the Pegasus TFU is specifically trained on TFU datasets. So if we exclude that dataset, we can see that Ernie performed the best for abstractive models. And now I'll pass it on to Dylan for more experimental results.
Okay, so this is an example of one of the speeches generated by our models, the T5, on George W. Bush's 2003 State of the Union speech. So we've determined that the T5 has generated a decent summary that accurately summarizes what the speech is about. However, it attributes it to John Avlon, who's a modern political commentator and a CNN anchor. We believe this is due to the fact that since T5 and many other models are pre-trained on the CNN Daily Mail dataset, they try to analyze the grammatical structure of these modern authors and compare it to the older authors in order to try to create a better summary. This leads to them creating good summaries, however, it could be attributed to the wrong person. Since we couldn't get golden summaries for the speeches, we weren't able to do rogue analysis on them, so most of our research was focused on TFU. In addition, some speeches were so large that our models couldn't analyze them as they required a limit to how many tokens they could handle. So here's a piece of TFU data that we analyzed. The original TLDR here is the human-generated summary that was written by the user that we used to compare as a golden summary for Rogue. And here are the summaries that were generated from that TFU. So notably, the best summary here is the Pegasus TFU, because since the Pegasus TFU was pre-trained on the TFU dataset, it knew what summary to make in order to get a good rogue score. So through our analysis, we've realized that since news articles tend to place relevant information near the beginning and the end, models trained on CNN and Daily Mail tended to perform poorly on the speeches and Reddit datasets, where, as Rick said, significant information is often spread uniformly throughout the text as opposed to weighted at the beginning or the end. And sometimes, as in figure 8, since Reddit TFU has no standardized posting format, sometimes users would put important information or main topic information in the title, whereas our models only analyze the main text and were not able to glean the most important details from it. As for writing styles, Reddit TFU is informal and often uses slang and broken grammar, whereas the State of the Union speeches often sometimes used Old English for the older speeches and outdated grammar that our models weren't able to recognize. Our models are trained on modern and professional news articles, so they have difficulty recognizing these two different writing styles. The variable writing style resulted in summaries that were drastically different from one another, with some being a lot longer and better than others. However, this leads to an advantage towards abstractive models, as human-made summaries are inherently abstractive, which leads to better comparisons towards abstractive summaries generated by our models.
So talking about some of the limitations that we ran into, one of our main limitations was regarding our computation in hardware, because a lot of these models have very large sizes. And because of the computation power that we had, we were only able to run those smaller model sizes. If we had ran their larger sizes, we're sure that we may have gotten better rogue scores. And as Dylan mentioned earlier, input size was also an issue because some of the speeches were way too long to enter into these models. As Dylan also mentioned, we were missing golden summaries for our State of the Union speeches, so we weren't able to run rogue on them. But there are ways to get golden summaries. One way that we read was to use Amazon Mechanical Turk, which is outsourcing your work to someone who would write these summaries for us. Or a lot of people use extractive summarizers to get their golden summaries and then compare them to the extractive summaries that have been created. Our final limitation was regarding language. We only did summaries in English, but Ernie, which performed best abstractively, actually does very well in Chinese as well. So that's not something that we researched. And style was also mentioned by Dylan. A lot of these models were pre-trained on news data sets. So when they were ran on data sets that weren't necessarily the same, it ran into it led to some differences. And now Varun is going to give you guys the concluding remarks.
So in the field of NLP, researchers mostly focus on new state-of-the-art models and developing new NLP state-of-the-art models. However, there is a limited understanding of current NLP models and what factors affect their performances. The second problem that we face is that NLP models are evaluated on the standard CNL Daily Mail dataset, which is not an accurate representation of most of the text or speech dataset that is available right now. So to solve these problems, we did two things. The first step was to do quantitative or qualitative analysis of our speech data sets, which were the State of the Union speech data set and the Reddit TIFU data set. And we did this quantitative analysis by taking the rogue scores. And from the rogue scores, we saw that the Pegasus TIFU model performed the best out of all the other models. The second thing was obviously analyzing on a variety of data sets like the State of the Union and the Reddit TIFU data set again. Now towards our results. I think. Okay, so for our results, there were two important things that we noticed. The first thing was that text data sets that had a large and varying writing style generally perform better for abstractive models, as shown by the high scores by the Pegasus and the Ernie models. And the second important result was that the performance of a model was heavily dependent on its similarity with the training data set, as shown by the Pegasus TIFU model. Now, this is what's currently happening in NLP. For the future of NLP and an area that we believe researchers should focus on, there are three important things we want to emphasize. The first thing is the availability of more diverse data sets outside the standard news domain. The second point is addressing the issue of temporality, which is the changing of speech or text over time. And the third is the ability of transformer-based models to read in larger amounts of text.
So that concludes our presentation. We would like to thank everyone listening for being such a great audience. And we'd also like to express our gratitude towards Brian, our research mentor. He was so inspiring and he gave us a lot of direction in this project. And finally, we would like to thank Brian and ACM Research as a whole for giving us this opportunity. Thank you. And we can now address any questions from the professors.
So let me go first again. So can you go to the slide on explain the bigram distribution that you were showing? Yeah, so what exactly are you trying to measure here? So bigram is those two-word entities.
Yeah, so I can answer that. So the bigram distribution basically shows where most of the information is concentrated in the text. So for the CNN, Daily Mail, and Newsroom datasets, most of the information is deemed important and relevant is more located in the front of the text, as seen at the x-axis, which is 25%. So the x-axis represents the location in the text. So the first 25% is much more higher than the rest of the 75%.
So you're looking at bigrams in the summary, and there.
This is just the source text so without the summaries.
Okay, so no, so I mean, so you're looking for specific bigrams, or I'm still not able to understand what this chart or these diagrams show.
So we wanted to see like where the distribution or where the concentration of information is mostly located. So for news data sets, it's more located in the front. So like,
but then you have to specify what that information is, right? So you had some bigrams in your mind or something, or that?
We just chose some general bigrams that were automatically selected from the data set.
Okay, so I see. So maybe most frequently occurring or something, and then you get the distribution. Okay. And then one more question I had is, so you mentioned extractive versus abstractive models. Can you quickly explain that one more time?
Yeah, I can explain that. So extractive models, as the name suggests, is taking words that are directly in the text and then just gluing them together in a summary. And then abstractive is looking at the text and then actually using words that are not in the text and then creating a summary out of those, which is more resembling of what a human would do, like when you read a textbook and then you create your own summary, like not verbatim, but on your own. So that's what abstractive does.
And where do those words come from, those other words?
They're just generated by the model, the vocabulary that the model has.
Okay. So at the end, you're still looking at, you have a data set of articles and their summaries, and then you learn a model, and then you apply it to a new article that shows up, right?
Yes, we train it and then we test it.
So the State of the Union addresses came with summaries, or?
No, they did not come with summaries.
So what did you do for those? You generated the summaries? I mean, so using them just as test data, not as training data. Clearly.
Yes, our research was mostly on the other data set, the TIFU, the Reddit TIFU data set. So yeah.
Okay.
Oh, wait, I can add on to that. So when we first started this project, we initially started on State of the Union speeches. And so we were able to run the models and generate summaries. But after we realized that we weren't able to time efficiently make golden summaries to compare these all, we added the Reddit TIFU in order to continue analyzing with something that could actually be compared to a human-made summary. But we thought the State of the Union data was interesting, so we decided to keep it in.
So final question, and that is, do you really think that machine learning will be good at creating summaries?
I mean, yeah, right now, the reason it's the CNN Daily Mail data set is because they have their own machine learning algorithm or models that generate summaries for them. However, that's just one of the many models that are available. So we wanted to study a lot of different kinds because, as you can see, the Reddit TIFU, State of the Union speeches, and news articles are drastically different types of text. And we wanted to study how different types of text would interact with these models.
I should just mention that in general, as humans, when we create summaries, we don't use this machine learning method by doing some kind of pattern matching. We actually understand the text and then create a summary. Yeah. So in my opinion, the technique, again, this is nothing to do with your presentation, but since you're talking about it and I'm a professor, I got to preach, right? So the technique that will really work is one where you create the knowledge out of the text and then use that knowledge to summarize. Anyway, I'm done with my question. So anybody else has, Professor Daescu or Cole?
Dr. Daescu, you are muted.
Dr. Daescu.
Did you have a faculty advisor on this project?
Oh, no. So we didn't have a faculty advisor. We just had Brian, who's, you know what, more than enough.
Well, I mean, Professor Gupta probably would have been a better advisor. So I just say sometimes it helps, especially it says you are tackling this NLP problem, right? And I mean, first of all, you look at this big companies that are doing NLP, and we have Google, and we have Amazon with Alexa, and we have Apple with Siri, and they are doing quite well, but they are not there yet to be able to do good summarization themselves. And then within the CS department, we do have a number of world-class experts in NLP. And I'm not saying that you did it wrong. I mean, you did a great thing and you just, pull it through by yourself. But having some good directions from people that have been doing this for many years would have definitely been helpful.
So Dr. Jessica Ouyang is the one who actually works directly on this problem using machine learning and deep learning for generating. So if you're interested in further work, you should talk to her. No, I don't work in, I work on using the knowledge-centered approaches where you try to understand what's there. Because machine learning, I feel, is a lot of pattern matching and correlations. And for some tasks, it's good. Like image processing for NLP, I don't know how good it's going to be, but anyway.
Thank you, Professor.
Yes.
Thank you.
So originally, Dr. Ouyang was supposed to be the advisor for this team, but it didn't work out.
Okay.
However, that is all the questions we have. Sorry, Dr. Cole, if you did have a question, but we have to begin moving on.
We just mentioned Chris Davis as well. Anyway.
Yes, definitely.
Advisor. Okay.
So the last team we'll have presenting tonight is the salient features in VR streaming team. Augustine, you're muted.
Yeah, I forgot. All right. Hello, thank you. I am Agustin Diogatis. We are the VR team. Today, Matthew View, David Wank, Natasha Tleas, Sunny Guan, and I will present to you our research on salient features in virtual reality viewport predictions. I will now pass it on to David, who will start us off with the overarching problem.
Thanks, Augustine. Streaming has rapidly become the most popular method of viewing video content, far outpacing old and outdated systems such as cable and satellite TV. With streaming comes new flexibility and possibility, such as the idea of loading 360-degree video that can be viewed with a virtual reality headset. But streaming also poses problems that other methods don't have that everyone is painfully aware of by now. Buffering. When a video can't load fast enough over the internet, it stops entirely. Virtual reality video, due to its high quality and large field of view, is especially susceptible to this problem due to the large amount of data needed. And when virtual reality's videos lag, the problem is worse than just irritation. People can easily get motion sickness from even the briefest of stuttering or buffering. However, there may be a possible upside. Since the user can only be looking at one section of virtual reality video at a time, because you can only see in a certain area, our research wants to explore the possibility of prioritizing parts of a video loaded by analyzing the correlation between a likely viewport, i.e. where a user is likely to be looking, and the existence of what we call salient features in a video. We call this process viewport prediction using salient features. Passing it on to Matthew to talk more about our abstract.
Thank you, David. Now, before we dive deep into our research, let me define some key terminology that you guys might be confused about. Starting with what a salient feature is. Salient features are the portions of a video that can be defined as a points of interest. Points of interest being something that you and I would be attracted to. And for example, imagine this. Imagine that you're in a VR headset environment and you're looking at a savanna, and all you can see is grass as far as the eyes can see. And then out of the left field of view, you'll see a herd of rhinos that come up suddenly, and your eyes are immediately attracted to these rhinos. These will be defined as salient features. Anything, basically what salient features are anything that can be defined, that could be moving, people, signs, or anything that really just catches your eye. And that could be defined as a salient feature.
Now, if we move on to the next slide, we can see, if we look at the figure above, we can see two types of circles. The large red circles represent the approximate location of the salient features, and while the orange circles represent the center of a user viewport that would be looking at the salient features. The correlation between the amount of viewports captured and not captured by this hypothetical viewport represents our correlation ratio. All of these salient feature traces and user viewports were collected from previous research efforts with Dr. Prakash's team, and it was really helpful. And now we can move on to the main point of our research, and that is viewport prediction. Viewport prediction is a method of predicting locations within a video where users will be staring at shortly before they actually do. And we can use this. We can do this by predicting by using edge detection algorithms to pre-process videos prior to the users viewing them. And we can utilize viewport prediction to prioritize data bandwidth to locations in a video where users are more likely to look at, saving a significant amount of bandwidth and help solve the previously mentioned buffering problems in VR. And now that we've defined some key terms, let me allow Natasha to explain our hypothesis.
Thanks, Matthew. So our hypothesis was that salient features can be used to predict user viewports, which can then be used to train a prediction model that can dynamically render important areas in higher resolution in order to reduce data bandwidth. This was based on the idea that users are more likely to look at salient features than other parts of the video. For short-term prediction timeframes, the viewports are close to the previous sample, and so as shown in figure 2. And so the prediction methods can be used. The current prediction methods can be used, but for longer timeframes, the prediction actually drops, which is why long predictions are more challenging. And this is why our hypothesis was that salient features will have more accurate predictions for videos that do not have user data. We then tested this hypothesis using a previous set of VR videos with complete data regarding the salient feature locations and viewport traces from 60 different users. To test this, we determined a correlation ratio to measure the accuracy of salient features. And this ratio shows how much salient features correlate to a previous user viewport traces. And for the second part of our research, we then created a prediction model that incorporates these salient features for videos that do not have user viewport traces. Now I'll pass it back to Matthew to discuss the two phases.
Okay, thank you, Natasha. So our research project involves two phases. One, a correlation proof that involves proving a correlation between salient feature traces and where users are looking at, as shown previously. And two, training a prediction model that to predict user viewport clusters based on salient features and on our existing user data that we've already previously obtained from our previous research group. And that's it for me. I'd like to pass it on to Augustine to talk about the methods and the results of our correlation.
Thank you, Matthew. So as previously mentioned, we needed to find a correlation so we can find the measure of the accuracy of the salient features, or in other words, the accuracy of finding the points of interest that the user is looking at. The way we determined our correlation for salient features was by the percentage of user viewports traces captured divided by the percentage of the screen that the salient features covered, as seen in figure 4. After running calculations on the videos, we found a medium to high correlation between the salient features and our viewport traces. We found that in mostly all cases, the correlation was greater than 1. This means that our correlation ratio is more likely to find a salient feature than by randomly choosing some area of the screen. Our goal is to reduce the bandwidth and to provide a smoother video experience. In figure 5, we are showing our coefficient interval, or how much we think will be the optimal amount of salient features captured by the different sized radii. We found that 50 to 75 pixels was the most optimal size of the correlation ratio. The larger the radius, the more the correlation trends towards 1. So if you think about it, this makes sense. The larger the screen, the more salient features we'll capture. However, the larger the screen, the more bandwidth will be needed. So we decided to stay with the optimal size that we found. Now, finding a high correlation means that there's a relationship between salient features and what the user viewport traces captured. Or in other words, the rhinos in the grassy savanna are going to get the most attention from the users. Now I'll pass it on to David, who will talk to you guys about other ways we found used our data.
Thanks, Augustine. Below is a table with multiple elements of data. First are some of the videos that we use to determine salient feature correlations on. As you can see, we have our base correlation ratios, which in some cases are high, such as video 6 with a value of 14, and in other cases are lower, such as video 18 with a value of 3.19. We then wanted to take a look at individual user demographics. For example, if a user is male or has never experienced virtual reality before, would they be more or less likely to look at a salient feature than someone who was, say, female or older than 25? We ran our correlation ratio again on these new individual groups of test subjects, and we then determined the difference between the correlation ratio resulting from that and the base correlation ratio. Some of those examples are shown in our second parts of the table. As you can see, most of our records actually don't provide a massive difference. For example, with our male subjects, you very rarely see a difference of greater than 5%, and for inexperienced subjects, you only once see any significant value. In fact, 68% of the records across all different possible user groups did not exceed a 5% difference from the base correlation ratio. So this doesn't exclude the possibility that particular demographics may affect virtual reality salient feature correlations in the future, but in the focus of our research, we found that there was no massive difference between individual user groups and the correlations for salient features that resulted. Passing it back on to Sunny, who will talk more about our future paths and the prediction model that we trained.
So the goal of our prediction model is to take a VR video and to compress it into a different VR video that still contains a lot of information, but is reduced in size so that users do not get the detriments of having motion sickness due to buffering. So for each VR video, we take it into individual video frames, and then we feed each frame into the prediction model, which will try to predict the areas that it should render to the user. Then, by comparing these areas to render and adding it onto the video frames, we can get a compressed frame. And a compressed frame will be smaller in size because lower resolution areas will be added to the areas that are not as important, and then the areas that are very important will be rendered in higher resolution. Then, by combining these frames into one video, we can get a compressed video, which can then get feedback to the user, and then they will have a much smaller file size, and then thus reducing the chance of motion sickness. So now I'll talk about how we train the model. So for training the model, we use a supervised learning with mean squared error as our loss function. For the inputs, we have two inputs, the salient features and the video frames. As you can see on the video frames, which are the second input, we have multiple layers. And each layer represents a different degree of detail. For example, one of the layers is using OpenCV's canny edge detection. Using edge detection, we found that users are more likely to look at edges because those are usually separating different areas that are very similar in color or similar in information. Then, by feeding in these different layers, and as well as the same features into our supervised regression model, the model will try to predict a cluster of XY coordinates where it thinks users will be looking at. Finally, we used the user viewport k-mean clusters that we got from our experiment data and compare it against these predicted clusters to get one final answer using mean squared error, which is our loss function. Finally, we feed these loss information back to our supervised regression model, which will then try to improve itself to minimize the loss and increase the accuracy. And on the next slide, we can see the prediction results of our prediction model. On the left side, you can see two types of circles. The green circles are where the model thinks people are going to be looking at, and the white circles are where the user viewport traces are clustered around. As you can see, the green circles are larger in size to account for the fact that users are usually looking at an area around the screen, around a certain pixel, rather than the singular pixel.
You can see that in this example, the green circles are all containing the white circles, which is good because that means if you just render the green circles, we would have contained all the information that users needed without having to render any of the other information. On the right side on figure 7, you can see the distribution for our loss function. The median is around 3,700 pixels squared, which comes out to around 61 pixels. And since our images are 500 by 250, that's around 11% loss. 11% is pretty good because going back to our example, users are usually looking at an area around the center of their viewport rather than at a singular pixel. And one example that we can know from this result is that if we render circles that only have 60% of the entire screen, we can get 90% of all viewport clusters. And that is very good because we don't have to render as much information, but we still retain a lot of the important salient features and user cluster centers. So some of our future directions are to improve our model using additional image processing layers, right? Because we talked about using edge detection, we can also add in a lot more different feature detection algorithms. The second one will be obviously to tune our parameters for our model to get better accuracy. And we can also combine with prior work on head tracking, which uses users' movement to predict where they're going to be looking at for short horizons. And fourth, we can also analyze the effectiveness across different video categories. For example, you have many salient features, you have one salient feature, or you have no salient features at all. And lastly, we can make an algorithm to dynamically upscale or downscale videos depending on where users are looking at, and therefore combining and finishing our network for turning a VR video into a compressed VR video that's ready for consumption. And on the next slide, we have our references. They have set out a lot of the groundwork for our research, and it would not be possible without their help.
And thank you, Sunny. Thank you so much. And I'd like to give a special thanks to our research advisor, Dr. Ravi Prakash. Without him, his previous research group's work, none of this would have been possible. We wouldn't have anything. We would have been a lot more confused in the beginning. And of course, Brian Ho, our great team leader, he was always there to help us, and he was always there to help us practice as well. And of course, Ryan Wu, the director of ACM Research. We wouldn't be having this presentation without him. So thank you, Ryan. Thank you. And yeah, that concludes, I think, ACM Research Night. It's great. And this is our poster as well.
Yes, thank you. Now we will open it up for questions. And I would like to start it off with Dr. John Cole, if you have any questions, because you did not get the chance to go last time.
Yeah, on the poster that I got, there was difference for male subjects, different for female subjects, and they were, like, for example, on video 3, minus 0.56 for male, plus positive 0.56 for female. And those are, exactly the same with the sign flipped. I guess you didn't include that on the one that you showed today. Was it really that different, male and female?
I can take this one. So when you think, we got our data for each user from a background questionnaire that Dr. Prakash's team handed to us. And the way our difference model worked was by taking the individual groups of users and comparing the result we got to the base model. So when you have a binary option, as was the case in male or female, because there wasn't a gender neutral setting.
Right.
So in the case of this possibly binary option, where it was either or, it ended up making a lot of natural sense that you would have equal but opposite differences from the base model. And that's because of this essentially duplication of data. We did end up cutting it from the final poster in our final presentation.
Okay, yeah, I can see why now. Okay, thank you.
Thanks, Professor Cole.
Are there any more questions? Oh, Dr. Gupta, I think you're muted.
I'm fine. I mean, this is great work. Everyone did wonderful research and wonderful projects. Really great work.
Yeah, this is very impressive, I must say.
Impressive, yes, yeah, indeed.
I would say the same. It's I mean, indeed, really, really nice to see all this effort you guys put in. if you only put in the same effort in a class,
This is
take algorithms or NLP or how great would that be? No, really, I mean, that's amazing. And this is because here you are following your passion and your interest, right? And I mean, hopefully you are putting to use things that you learn in classes. Let's say you did a great thing indeed.
So one thing I would add is that, you should let Michelle Posamentier, who's our departmental writer, know about these things. Now I see that you're recording it. I mean, you can have a story written and posted on the department website. I mean, this will really be great for the department, great for ACM, and great for everyone, all around. So I'll send out an email and introduce everyone so that Michelle can actually write a story. And the same thing for ACM projects, I guess, that was held, 10 days ago. Should write a story on it and put it on our website.
Dr. Gupta, I have something to follow up about this. So we actually made our poster completely separate from our presentation for the sole purpose of having it printed and posted on campus. So would Michelle have anything to do with helping us out with making that a reality?
No, sorry, I did not quite. No, Michelle generally just write, if you go to cs.utdallas.edu/news, she writes stories, press releases, kind of, you can think of them as. So it'll be great if we saw a story on the department website about this whole event. That's what I was alluding to. I was not asking you a question or making a comment about your project in general.
So Michelle won't be able to help you with producing, like printing the posters or displaying the posters on the hallway.
Oh, I see. I mean, no,
that's not her.
Yeah, so that would be actually Dr. J can help put them in the hallway. Yes, that's a great idea too. Put these posters in the hallway. I mean, that would be fantastic. So Dr. J, so I'll again make introductions and Dr. J can help. So he's the one responsible for putting all those posters that you see across from the open lab. And it'll be great to have them actually displayed. I mean, it really shows to the whole world, what we are doing, what you guys are doing. And again, this is, I mean, just fantastic. What ACM Research, ACM projects, all the stuff that you guys are doing is simply fascinating.
Thanks, Dr. Gupta.
Yes. So that's all the questions we had. And that's all the presentations we also had for tonight. I'm going to share my screen now. So awesome. So yeah, like David mentioned about the posters. So the original plan was, so hold on. Okay, that's the end of the presentations. Judges, please take like a couple of minutes to verify your rubrics and scores. Make sure your scores are filled out. And then while we wait, I'm going to talk about the posters. So originally the idea behind ACM Research was that each team would create a poster. And so I had planned ACM Research to be in person, but that didn't work out because of COVID. So how it was supposed to be structured was each team would present their project, and then the audience and the judges could take a minute afterwards to walk around and see the posters. Unfortunately, that can't happen since we're in a virtual environment. We can't show up in person. But each team has, they did make a poster and they were posted in the GitHub. I will attach that into the chat. I highly encourage y'all to check out the posters each team have created. It is located in the separate repos for each team. They've put in a lot of work into the posters and presentation. So yes, please do check that out. Yeah, we're going to take a couple of minutes for the judges to finish up scoring, and then I will be announcing the first place winner. Judges, please let me know when you have finished grading, but no rush.
So I finished mine. I wrote down done at the bottom. Can I just close the document?
Yes, you are good to go, Dr. Dasku.
Okay.
I see your rubric.
So.
And once we get all the scores, I'm going to count them all up, and I will announce the winner. We will see momentarily.
And the winners, they get a prize? They don't get any prize?
Yes.
How is
So the winners, I don't believe I mentioned it, but the winners will be, each member of the winning team will receive a $25 Amazon gift card that will be sent via email.
As this, they don't get it tonight, so they don't have time to use it. It's still Cyber Monday, right? Amazon has great deals. So most of the students here, you guys are seniors, juniors. What is the level you have?
I'm a sophomore. Well, everyone on the VR team is a freshman except for Matthew and Brian.
Freshman. Oh, freshman. Oh, so you have lots of time to do research then.
No, okay, David, you're wrong. We have one junior, one sophomore, and two freshmen.
Okay.
And two sophomores, two sophomores, one junior, and two freshmen.
Okay.
There's a lot.
How about the other teams?
Analyzing phishing attacks had three or four freshmen and then one junior.
Wow, that's impressive. So all these things are done by freshmen and sophomore with some help from juniors, no seniors. You want to keep it young, okay. So that's amazing because you'll have plenty of time to get engaged in research, right? So 2 more years, 3 more years, some of you, at least 2 more years. So take advantage of that. And you can try, to continue to do it by yourself. You can try to get involved with some of the faculty labs we have here. I mean, definitely some of you are working already, like with Dr. Prakash and with Dr. Gupta or others. But yes, keep these things going because you have time to do great things. And in fact, some of you might become entrepreneurs by the time you are ready to get a bachelor degree. You might start your own company.
Okay, the judges have filled out their scores. Thank you. I am now going to add up the scores, which will take a second. I have to use a calculator. Very sad.
It's hard. Yeah.
I should say that y'all are winners. Really hard to tell. It's just random. All of you did a great job. I mean, I don't know who should I pick as number one, honestly. So.
So Gopal, I see the book behind you, How to Reason.
Yep.
There you go. The right book at the right time.
Oh yeah, that's actually by a psychologist.
Yeah.
Okay, I have calculated the scores. It was very close.
I bet.
Like 1 point close.
Wow.
Okay, I'm gonna now share my screen.
You might have to do a recount.
I did do a recount just to make sure.
We're gonna challenge the results.
Challenge the results.
Yes. So, So yes, for tonight, we only will have one first place team winner, and then each member of the winning team will receive a $25 Amazon gift card. The criteria for judging included abstract, poster content, poster appearance, quality of analysis, and the presentation of research. I know some of these teams didn't have their poster, but I did send posters to the judges beforehand.
Yeah.
Now I will now announce the first place winner. The first place winner for the first ever fall 2020 ACM Research Symposium. Y'all, it was very close. 1 point difference, and I needed to. Of course, I recounted it. But the moment y'all have been waiting for, the first place team for ACM Research for the fall 2020 semester is the Phishing Attacks team.
Phishing attack. There you go.
Yes.
Well done, guys.
Congratulations.
Well done. Congratulations.
Now, don't be discouraged for the rest of y'all that didn't win. Every one of y'all did an amazing job this semester, and you're.
Yes, indeed.
But yes, that concludes the first edition of the ACM Research Symposium. Thank you to our judges tonight, Dr. Gupta, Dr. Diascu, and Dr. Cole for helping out, and very special thanks to our only faculty advisor, Dr. Prakash. To the audience, thank you for coming out. We hope you enjoyed the symposium and what all the teams had in store. Again, I highly encourage y'all to see each team's posters in our GitHub. Yeah, that is all. Thank you, everyone. Have a great night.